Well, ladies and gentlemen, let's get on to the innovation that we can now harness for intelligent data management. The Aerospike Vector and how it facilitates in unleashing the potential of AI from Mr. Ashish Shinde, Director of Engineering, Aerospike APJ.
Hi everyone, good afternoon. I'm Ashish. I work as an engineer at Aerospike. Today we are just going to look at one of the new products that we are launching. It's called Aerospike Vector Search. It continues on the theme of Aerospike foray into the AI world. So we look at, so basically what we'll do today is do a general introduction to vector search and also look at some of the key features of our implementation of vector search. I guess through the previous talks, we would have gotten some idea of what's the potential of AI, how do you use it for your use cases. But just to provide an introduction to people who are not very familiar, what I'll be doing is just talking a bit about what is vector search and look at some of the use cases. So we'll start off by basically contrasting vector search with what we are traditionally used to, which is labeled in this slide as traditional search. So we are all familiar with how it works. Typically, traditional search works with text data. You have a single text box. You have data which is annotated. So for example, this is a search illustrated for an e-commerce platform. The search phrase is blue bag. And what you see on the left is the result that might be returned from a traditional search implementation. So here you see that there are a bunch of blue bags that are listed. But the way the traditional search works is it's based on keywords, associated tags, and labels that have been ingested along with your data. That's one of the ways traditional search works. The data could have been scraped from the web, could have been crawled using some API, or could have been manually entered. But all of it relies on having high quality annotated data. Whereas what you see on the on my left is something which is powered by a vector search application. The way vector search works is instead of relying on structured labeled data, you could have unstructured and data which does not have enough labels. For example, here you could have just ingested a product catalog as a bunch of images, and you could have your vector search or your search being powered based just on the content of the images. So what we see here is the results which is returned by a demo application which is built on top of our vector solution. It's the same search phrase, which is a blue bag. But what you see here is the results that are returned do not exactly match the text or the associated tags with the images. So there's a turquoise bag which is returned. There is some similarity between the color turquoise and blue. It's a variant of blue or a shade of blue. So that is something which the traditional search would not be able to capture unless you have very highly annotated data or manually curated data. That's something which vector search can bring to the table, where it could create associations or ways of doing search beyond annotating or labeling data. So we'll just look at some of the use cases where you could employ vector search. One of the ones we just saw a small snippet of, which is similarity search. So what vector searches can allow you to do is have your unstructured data, and basically you could search for similar data items based on your inputs. The unstructured data could be images, they could be text snippets, they could be videos, or they could be audio files. So any unstructured data could be used, and you could search similar items. So you have seen some of these applications very common. For example, there are applications where you could give a music snippet, and they'll give you similar types of music, or you'll find online image search applications where you could give an image of one object and you would get other similar images, etc. So that's what is similarity search. That's one of the popular applications. The other application, which is again driven by similarity search, is medical diagnostics. So you could, for example, have X-rays or scans and then classify them as malignant or benign, just based on image similarity or similarity that you have trained your data models for. Other popular use case could be fraud detection. Again, this could be identity theft, where you want to detect duplicate identities. You want to detect frauds based on transaction histories or particular parameters of a particular transaction. You could also build recommendation systems using vector search. So this is also another popular use case on e-commerce platforms, where you might have access to users' search history or his buying history, and you might be able to, based on profiling the user, recommend a new set of items that the user could look at or potentially buy. The last use case I think has been talked about in the previous presentation as well. It's called RAG for short, Retrieval-Augmented Generation. So this is where you could use the generative AI models and power or create applications like chatbots or support systems. So look at some of these in details. So what this slide shows is generally the workflow that is associated with use of vector databases and similarity search. It all starts with unstructured data. Like I said, the unstructured data could be images, videos, documents, audio, or any other form of user-generated data. The key bit in vector similarity search is to transform your unstructured data into what we call vectors. Vectors are typically the things that we study in probably schools and colleges in the mathematical sense. A vector is an n-dimensional array of numbers. So the key step here is you take your unstructured data and convert it into a vector, n-dimensional vector. The key property that a vector transforming model would have is items which are similar in the human sense or in the input sense would end up in vectors which are close together in the vector space. So that is one of the key aspects of the models that you use for creating these vectors or vector embeddings. So the workflow is you have unstructured data, you have a model. So for images, you could use open source models called like Clip. You could use LLMs as well for generating embeddings out of textual content. So you could transform them into vectors. You store it into a vector DB. This is a solution that Aerospike has built. It's available for trials, and it will soon be GA'd. And that is what is called your vector storage. The way you would use this data once you have vectorized your data and stored it into a vector DB is to perform queries based on, again, unstructured data. The unstructured data could be images, so you could provide this particular vector search image, convert it into a vector form of that image, and then query the vector database for similar images. So that is the key pipeline that you would use along with a vector search. And these would typically be the steps where the key component would be the model and the vector database. I think the previous talk also covered some of the issues that we have with RAG, but just to illustrate, this is one more use case where you could leverage vector databases, and that too at scale. So on the left, what we see is, again, it's an inbuilt application that we have built for illustrating and testing out our vector solution. On the left, what you see is basically the data set for this application is our Aerospike documentation, user documentation. On the left, what you see is data, a query which is answered purely based on a LLM, which is Llama 2 model. And on the right, you see the same query answered by Llama 2, but the query has been augmented using our vector database to avoid or to work around some of the pitfalls that you have with LLMs. So in this particular case, right, the LLM has hallucinated, and for those of us who are familiar with Aerospike, you'll know that the last step is not correct. That's not what is required to be done when you create a secondary index. That's something which the LLM has actually hallucinated. The same prompt, if we had done some amount of prompt engineering, we get better results and more relevant results. I think this has been talked about, but yeah, just to go through the steps, this is how you could use a vector database in the RAG context. You have your user prompt, you convert it into a vector, use your vector store to get more relevant or more recent information from your core data source. and then use that retrieved data to engineer your prompt better so that your LLM can generate more relevant or better responses. Now we'll move on to how Aerospike Vector Search works. The Aerospike Vector Search has two components. It's basically a clustered distributed vector storage database. You have the product architected in two layers. There's a compute or a search layer, which is where the index generation for vector search happens, similarity searches, queries are answered in that layer, even index building happens in the compute layer. And then we leverage Aerospike key value store for storing the vectors as well as the indexes that are associated with vector search. So this, with Aerospike Vector Search, right, one of the key things that we have tried to make sure that our solutions handle is the ability to scale horizontally as well as vertically. This is something which is very specific to our vector search solution. If you compare it with other vector search products, we do have ability to scale horizontally and vertically, both in terms of ingest as well as queries. Lot of these reasons come with the way we have overlaid the indexes onto Aerospike storage. The key aspect here is we don't actually partition the data. We rely on building single indexes, which gives us some performance advantages while ingest as well as queries. So the key bit here was that we have access to a very high speed, low latency, high throughput storage layer. This is just a quick slide on how Aerospike Vector implementation is different. Basically, we do provide high throughput at very low latencies. Our storage is scalable. You can tune it to different workloads that you have. You could tweak completely from going all flash to completely in memory based on your storage sizes as well as your throughput needs. It does support thousands of dimensions. You can scale out the QPS both for ingest as well as queries by adding more nodes. And our latencies based on your data set number of dimensions range from a single digit to double digit. So these are some of the key performance highlights that we have. It's still a work in progress, but we are very close to a GA. We do allow a very flexible model in which you can use your vector pipeline. One of the key features of our vector solution is you could stream updates and deletes. So one of the common problems that you have in the vector database landscape is as your data changes, how does the performance, both in terms of query performance as well as accuracy of your results, be maintained. So that is something which we have worked on. So the model that we have with our vector solution is not batch load and query. It's a continuous model where you could stream in your updates, stream deletes and new inserts, while still doing queries online, and the system will self-heal and manage the indexes. Because our storage is leveraging Aerospike, it comes at a very low TCO, and you have flexible options for managing your TCO as well as spent on hardware. We'll just do a quick demo. I think you guys, there's a booth setup where you could actually look at more demo applications which are built around our vector search product. For the demo, I would be I'll be showing a simple image search application that we have built using our vector database. This particular application actually indexes a whole bunch of open source image data sets. The input to this demo is only a bunch of images. They are not being annotated in any other way. It's just plain images. We use the open source clip model for converting these images to vectors. But then you could see the power of vector search. Basically, the input to this system is just images. It's not annotated data. And if you see this particular page, what I have done is I have done a query for a red bird. So somehow the vectorized images have been able to capture the fact that these images have red birds. The text prompt, which is red bird, has also been vectorized, and that's the vector search that has happened. So you could see the power of doing vector search. This demo also shows the times that it has taken. Like it's slightly, the query times, etc., are slightly bloated because the application is running in US. So we also have the network latencies involved. But you could do a whole bunch of plain text searches, or you could do search by image. So I could, for example, pick one of these images and say, give me images which are similar to this image in the database. So that's something which vector search as well as Aerospike vector solution allows you to do. You could, for example, keep on navigating and picking out more similarity searches. You could do again text-based search and say, I want images of, for example, a white cat. So the point to note here is that the data has in no way been annotated with any text. This is completely coming off the images that have been vectorized. So that's actually the end of the presentation. We do have a demo booth set outside where you could actually look at these applications, get into more details, and even figure out how to get hold of or start using the Aerospike vector search. Thank you.